Hi everyone, it's Mr. Baker here with another physics video. Today we're going to be looking at nuclear fission. So today we're going to be looking at nuclear fission and we're going to be answering this question: what is a nuclear bomb? So nuclear fission. So we talk about induced nuclear fission and that occurs when a stable isotope is struck by a neutron. So induced kind of means something that is man-made, something that wouldn't happen naturally. So it's something that we have made happen. So induced nuclear fission occurs when a stable isotope is struck by a neutron. The isotope absorbs the neutron, becomes unstable, and then splits into two smaller fragments, releasing large amounts of energy and 2 or 3 neutrons. Okay, so fission is the splitting of a nucleus into 2 other parts and 2 or 3 neutrons. Induced fission is not a natural event, as I said. Very rarely fission occurs without a neutron being absorbed. This is spontaneous fission, and just as induced fission, the nucleus splits and energy and neutrons are released, but for a chain reaction to occur, isotopes must be fissionable, or a fissile material, and we'll look at what that means. Okay, so let me show you a little animation of what happens during nuclear fission then. So the blue things are neutrons and the red things are protons. And we can have different types of uranium that might fission. So here we've got uranium-237. We've got a neutron being absorbed by the nucleus. The nucleus then splits into 2 smaller sections, and 2 or 3 neutrons are also released. And so the 2 elements that have been produced, the nuclei of these elements, so we've got krypton and barium. Let me show you that and have a look at the equation as well. So the nucleus is absorbed by the uranium, and in this case we've got uranium-235. So uranium-235 plus a neutron goes to be uranium-236. So it's still uranium. You can see the proton number, the atomic number stayed at 92, but it's absorbed a neutron, so the atomic mass has gone up by 1. So that makes it unstable, and so it splits, and it splits into barium and krypton, and 3 neutrons as well. So let's carry on looking at it. So enriched uranium is normally used in nuclear reactors to ensure chain reactions will be sustained. Naturally occurring uranium is 99% uranium-238, which is non-fissionable. To enrich it, 2 to 3% of uranium-235 is added, which is fissionable. Plutonium-239 can also both be used in different nuclear reactors and in nuclear weapons as well. And this is really interesting, that the fission of 1 kilogram of uranium-235 releases more energy than burning 2 million kilograms of coal. So you can see why people might want to use nuclear fission, nuclear reactors, rather than coal power generators, because we can use 1 kilogram of uranium instead of 2 million kilograms of coal. There are other advantages as well, which we'll look at. So we've looked at one fission reaction here. So that releases some energy, but for this to actually be something that we can make electricity from, we need this reaction to happen over and over again, and that's what happens in a chain reaction. So in a chain reaction, we have a neutron being absorbed by a nucleus of uranium, which then splits into 2 smaller nuclei and 3 neutrons. Those neutrons then go on to be absorbed by other uranium nuclei in our fissionable material, which then split, and each of those split into 2 and release 3 neutrons as well. Those then go on to be absorbed by more nuclei, which split and release more neutrons. And this goes on and on and on as long as there is fissionable material for this to happen. So let's break that down then. So nuclear fission results in a chain reaction because each time a nucleus splits, it releases more neutrons. These can go on and cause more fission reactions to occur, and more and more and so on. This is why a chain reaction releases a lot of energy so quickly. If a chain reaction is uncontrolled, heat builds up very quickly. A chain reaction must be controlled to maintain a steady output of heat. And that's what happens. So we control this in a nuclear reactor. And we'll just quickly look at how electricity is produced in a nuclear power plant. It's very similar to a thermal power plant that might use coal, oil, gas, or biofuels. So, and the only difference is that we use uranium fuel rods instead. So down the bottom there, you can see in our nuclear reactor we've got some rods. These are the nuclear fuel rods that contain the uranium, and the neutrons are being absorbed by the nuclei, and then it's fissioning, and it is then creating heat. So that happens. The heat then boils water. The water turns to steam. The steam turns to turbines. The turbines turn the generator. The generator makes electricity, and then the electricity goes to the national grid and powers our homes and our businesses. So it's exactly the same as a thermal power station, apart from that very first part where we use nuclear fission, the splitting of a nucleus, to produce the heat that is needed to boil the water, to turn to steam, to turn a turbine, to turn a generator, to make the electricity. Okay, so let's have a look at what happens in a nuclear reactor in a little bit more detail. So on the right hand side here you can see a reactor, and let's have a look at these different parts. So we've got the fuel rods. So these orangey red bits here, they're the fuel rods, and the fuel rods are where the uranium is. Either side of the fuel rods is the graphite moderator, and I'll explain what that does in a second. The whole thing is in a pressurized vessel, and then around the outside there's this radiation shielding, which probably consists of meters and meters of concrete, maybe some lead and things like that, because we're talking about nuclear reactions here. So there's going to be some nuclear radiation that's released, and we obviously don't want that to go and contaminate anything else. And then at the top we've got these things that can move in and out. You can see there's some that are up and some that are down here. These are the control rods, which we'll look at what they do in a second as well. So we've said that for nuclear fission to happen, a neutron must be absorbed by the nucleus of the uranium. High-speed neutrons won't be absorbed, they'll just bounce off the nucleus. So what we've got to do is we've got to make these low-speed neutrons. So we use the graphite moderator. So the neutrons are released, and then they've got to go through this graphite in order for them to get to the uranium. So let me show you a little animation of this. So you can see here neutrons being released, and as they get to this graphite, which is the blue stuff, you can see they bounce around inside the graphite and then slow down. Then they can move off as slow moving neutrons, which are then readily absorbed by the nucleus. So that's what the graphite moderator does. It slows down because the neutrons bounce around inside and lose energy as they bounce around inside the graphite moderator. They're not absorbed by the graphite, but they just get their energy is absorbed, so they slow down, and so those neutrons can carry on going as slow moving neutrons, which are then absorbed. But without controlling how many neutrons are absorbed by the nuclei of the uranium, then there would be this uncontrolled reaction, and it would be very much like an atomic bomb. So we use these things called control rods, and they're made of boron, and they absorb excess neutrons to prevent chain reactions from getting out of control. So a steady state induced reaction will occur when control rods are used to ensure that one neutron from each fission goes on to produce more fission. This makes sure that energy is produced at a steady rate. So by moving the control rods in and out, you can control how many neutrons are then being absorbed by the nuclei of the uranium, and then you can control how much electricity ultimately you are producing, because you're controlling the reactions that are happening. Fission neutrons are also slowed down by water, so you can see on the right hand side there those arrows, and those arrows moving up towards the right and then out again. That's showing the flow of water flowing through the reactor, and the water is also used as a coolant, taking the kinetic energy of the neutrons and transforming it into heat used to produce electricity. So neutrons that are being released by the fission reaction are then absorbed by that water. The water then heats up, and then, as we've said, the water then turns to steam. The steam then turns to turbines, turning the generators, and then makes electricity. So that has been our lesson on nuclear fission, and these are the things you should be able to do. So you should be able to describe what nuclear fission is and distinguish between induced fission and spontaneous fission. You should know the differences between naturally occurring isotopes and enriched nuclear fuels, and know the key components of a nuclear reactor and know what those bits do. You should be able to explain what a chain reaction is, and you should also be able to explain how a steady state induced fission reaction can be maintained. But at the start we asked, what is a nuclear bomb? We kind of talked about it a little bit during the clip, but we've also talked about a steady state nuclear fission, and this is where fission is controlled by excess neutrons being absorbed by the boron control rods. A nuclear bomb is uncontrolled. It allows a chain reaction to go unchecked, causing all fissionable material to fission in a very short amount of time. All of that energy is then released very quickly, creating a massive explosion, as well as the release of nuclear radiation, and that can be dangerous for long after the explosions have subsided. So that's been all about nuclear fission, and I've been Mr. Baker, and I will see you next time. Thanks very much.